All right, this is 2010 Form B, question number 4. It says a squirrel starts at building A at time t equals 0 and travels along a straight wire connected to building B. For the time interval from 0 to 18, the squirrel's velocity is modeled by the piecewise linear function defined by this graph that's over here. So this is the graph of the velocity. So obviously the velocity is increasing, then constant, then decreasing, so on and so forth. It says, at what times in the interval from 0 to 18, if any, does the squirrel change direction? Give a reason for your answer. Now remember that not only is velocity increasing, so on and so forth, but it also indicates direction. So a positive velocity indicates that the squirrel is moving to the right, and a negative velocity indicates that the squirrel is moving to the left. So you can imagine positive being that it's going towards building B, and negative being that it's going away from building B, or back towards building A. So because this first interval right here is positive, that means that the squirrel is going towards building B, and then right here it has a 0, so that means it changed direction and it started going back the other way. So now that it's negative, it's going back towards building A again, and it's negative for a bit, and then again it changes direction and it goes back towards building A again. So it changes direction twice, and that happens at both of these zeros, at 9 as well as at 15. So you get 2 points for that. You get 1 point for saying that it occurs at 9 and 15, and 1 point for the explanation of the fact that the squirrel changes direction whenever its velocity changes sign. So from positive to negative, or vice versa from negative to positive. Part B says, at what time in the interval from 0 to 18 is the squirrel farthest from building A? How far from building A is the squirrel at this time? So it's probably pretty obvious just by looking at the graph where this occurs. So if you think of like position, right? Because this part B is asking about position. How far is it from the building? And so if this is the graph of velocity, position would be the integral of that, or in other words, the area under the curve. So if you think about the area under the curve, this big trapezoid right here is a pretty big area. And then this little trapezoid down here is negative, so we're going back towards building A, but not as much as we went towards building B to begin with. And then this little tiny shape over here as well takes us back towards building B. But obviously the trapezoid, or the shape with the biggest area, would be this one. Now you have to be careful with these ones because they actually want you to identify what the possibilities are. So we need to look at all the critical points as well as the endpoints and prove to ourselves, not just by observation, because observation is a good way of checking to make sure you're getting the answer right, but observation is not the only way that you can show your answer. And so essentially to figure out, when it's the farthest, it should be at t equals 9 because it's accumulated all this area in between 0 and 9. However, let's prove to ourselves that that really is the answer. So we know that it changes direction at 9. We know that it changes direction at 15. So those are two possibilities for the farthest from building A, but also the endpoints. So at 0 as well as at 18. Those are possible solutions as well. So if we look here, we need to identify the candidates. So it could be at the endpoints at 0, it could be at 18, or it could be at these two critical points in the middle at 9 or 15. So we just have to find the area under the curve. So at 0, it's at 0 because they're starting at building A. And then I calculated the area under this first part, and that was an area of 140. And then the area of the second part was an area of negative 90. I'm sorry, not negative 90, negative 50. And so 140 minus 50 was 90. So that's how I got 90 right there. And then last but not least, you add on 25 more to get back to the end again, which is 115. So again, I think it's pretty obvious just by looking at the graph that 9 is where you're going to be the farthest away from building A. And so that's the answer, t equals 9, and it happens to be 140 units away from building A. However, again, you need to be able to show the candidates to show that you're analyzing all possible options and not that you just got lucky with one of them. So show all the possible options, including the endpoints as well as the critical points, whenever they ask you to find a maximum or a minimum, or an absolute maximum or an absolute minimum, I should say. And that one's worth 2 points. So you get 1 point for identifying all 4 of the candidates, and you get 1 point for having the answer that 140 is the maximum distance away. Part C. Part C says find the total distance the squirrel travels during the time interval from 0 to 18. Now, this question has one keyword in it that if you miss this one keyword, you could totally get the answer wrong. And you might think, oh, this one's super easy. We already answered this question. Because if you look down here at part B, we already figured out that the area under the curve from 0 to 18 was 115. Okay, so you might think, oh, this is super easy. We already figured it out. Great. There's one problem, and that's this word right here. This word means something different than this value. Okay, and here's why. This value, 115, actually represents what's called the displacement. So hopefully you've heard of that word before. So again, this is the displacement. And so the difference between displacement and distance is that displacement says where did you start, where did you end, and what's the distance between those 2 points. Whereas distance means where did you start, then where did you go, then where did you go, then where did you go. So it wants to keep track of everywhere that you went and count all of those distances. So for example, let's just pretend that, we have a little map here, and you start at your house, and you go down the street to your friend's house, and you go across the street to the 7-Eleven, then you go across the street to go to Denny's, and you go up here to go to the movie theaters, and you come back over here, and then you wind up right here at, I don't know, let's say the skating rink or something. So you started here. Obviously the distance between these two places where you started and ended is not very far, and you could find that distance easily. That distance is called the displacement. So this specific length here, let me do it in a different color. The specific length here would be the displacement, all right? However, the distance would be keeping track of everywhere you went. So you'd want to add together all the different areas. So here's how that applies to this problem. That applies to this problem because when the squirrel started going towards building A, we were accumulating all that area, but then all of a sudden when he started going backwards, we subtracted that area, we took away that area. We don't want to do that. So you actually, in order to solve this problem, want to look at it as the absolute value function. So pretend like this function is actually up here, not down here. So when we add together the areas, we're actually going to add them all rather than subtracting that piece. So we can calculate, adding in all the areas no matter which direction you're going. So when we do that, come back over here, we get that the integral from 0 to 18 of the absolute value of the velocity function is 140 plus 50 plus 25, which ends up being 215, not 115. So kind of keep that in mind, that it's the distance versus displacement, and distance is everything versus displacement is just the starting point minus the ending point, or vice versa, I should say. So that's part C. Let's see how many points you get for that. Part C, you get 1 point for that. So you get 1 point for the answer of 215. All right, last but not least. It says write expressions of the squirrel's acceleration a of t, velocity v of t, and distance x of t from building A that are valid for the time interval from 7 to 10. So if we look closely over here, actually, I want you guys to notice that 7 to 10, I'll highlight it on the x-axis and on the actual graph. 7 to 10 is this interval right here. And if you look at it on the actual graph, that's just this line right here. So essentially they want to know if this is the velocity function. Number one, find the equation of that line, because that'll give us the equation for the velocity on that interval. Number two, take the derivative to find the acceleration, and that'll give us the formula or the equation for the acceleration. And number three, take the integral to figure out what the position was. So let's look at all three of those. Number one, this is a straight line. So in order to calculate the slope of a straight line, you can either just count rise over run, or you can actually put it into the slope formula. So I did that actually, so I'll show you guys how I got that point. So over here, all right, I did a couple things. Number one, I figured out the slope of the line by just doing y2 minus y1 over x2 minus x1, and I figured out that the slope was negative 10. So I plugged it into point slope formula, and I used the 0.7, 20. So I plugged it into point slope formula. Remember that I'm always okay with you guys leaving your answer like this. And I'm sure that on this question that they would be completely fine with that as well, because technically it's a correct answer. However, notice that you're going to have to take the integral of it and the derivative of it. So you might as well just put it into slope-intercept form for this one, just because it's easier to take the derivative and integral that way. So I figured out the equation, I figured out and put it in slope-intercept form. And now this is the same thing as my velocity equation. So essentially I found the formula for velocity, or the equation for velocity in between x equals, or t equals 7 and t equals 10. Just notice that I changed it over to a t because we're talking about time. So velocity is the first derivative, the acceleration is the second derivative. So if I take the derivative of velocity, I get negative 10, and that's the acceleration formula. And then I have to take the integral of the velocity function to get the position function, because remember that's going up. So the integral of negative 10t plus 90 is negative 5t squared plus 90t plus c. Now, we can't leave a c here, so notice that I put a box around my answer, but that was only temporary. My actual answer is right over here. And so I have to use an initial condition. So I already knew that up in part B, we figured out that one of the points on the original graph is 9, 140. So I just used that one. You could use any point on the interval from 7 to 10 if you wanted to, but I just used this one. So when you do that and you plug it all in, this initial condition, by the way, you have to choose one that's on the interval from 7 to 10. So you couldn't choose one on the outside of that. So you plug everything in, and I simplified and multiplied and all that good stuff and got negative 265. And then after I did that, I plugged it into my original formula and got negative 5t squared plus 90t minus 265. And that was the position function. So that was worth 4 points. You got 1 point for getting the acceleration, 1 point for getting the velocity, and because you had to do a little bit more for the position, they gave you 2 points for the position. So if you had difficulty finding that c value, I'm sure they would have given you 1 point just for finding the general integral, and then finding the c value is where you probably would get that last point. Perfect. So again, that was 2010 Form B, question number 4.